Okay, so this is a mini lesson about chapter 8, which deals with similarity. Basically, in this section, we're going to be able to find missing sides and angles in similar figures through setting up a proportion of two equal ratios. We're going to identify why two triangles are similar, and then we're going to be able to use proportion to find missing sides and parts and various other kinds of problems setting up proportions. Basically, if you remember similarity, you remember that we've talked about this, and same shape, different size is the phrase that you've heard over and over. So similar figures look the same, they're just not the same size, okay? If you're reading that blue part at the bottom, number of problems were taken from the review packet, but the numbers within the problems were changed. So you'll be able to follow along in your review packet, and when we do a question, you could try the corresponding number in your packet because it wouldn't be the exact same answer. You could have a little bit of extra practice that way. All right, so first question that we're going to look at is numbers 1 through 4b. And basically, this is a good question to really tell you what similarity is. Okay, similarity, same shape, different size. Okay, similar figures, triangle ABC and triangle DEF. Similar figures have some main things that you need to remember. The first thing is that corresponding sides have equal ratios. That's an important concept, and that's going to help us set up proportions in a second. The second main point is that to find missing sides, you need to set up a proportion, which again is an equation of ratios. Ratios are just fractions, or a quotient of two numbers. And then lastly, corresponding angles of similar figures are going to be the same. Okay, that's what gives them the same shape, is their angles remain the same, but their sides are different. Their sides are different by the same ratio, and that's why we can find missing sides. So the first question is, what is the scale factor of triangle ABC to triangle DEF? And scale factor is very simple. It's just a word that means the ratio between corresponding sides. If we look at this picture, and the corresponding sides that we recognize right away are 6 and 5. AB corresponds to DE. AB is 6, DE is 5. Therefore, it's a very simple ratio, 6:5. If you want to write it like that, you can write it like that, or you can write it as a fraction, 6/5. All right, if this was a fraction that was reducible, for example, like 6/4, you'd have to take out the greatest common factor and reduce it accordingly. All right, so that's your scale factor. And actually, that is important because that's the number, that's the ratio that we want to use to find missing sides. Because we're going to be able to figure out AC in part 2 and EF using that scale factor that we just found in part 1. So first thing, I'm going to find AC. Okay? Now looking at the picture, I can see that AC, we'll call AC X. AC corresponds to 8. So X corresponds to 8. Well, we already know that 6 corresponds to 5, so the setup is very simple. 6 corresponds to 5, or 6/5 equals X over 8. And that's the proportion I want to set up. So then I cross multiply. 5 times X is 5X. 6 times 8 is 48. You divide both sides by 5. X ends up being 48 divided by 5, which I believe comes out to 9.6, but let me just check it in my calculator. It does. X is 9.6. So that's the answer to AC. Okay? We're going to do a very similar thing to find EF. We'll call EF Y, just so we don't get it confused with AC. And I can see right away that BC, which is 9, corresponds to EF, which we called Y. So the setup for that one is going to be very similar. So if I'm looking for EF, okay, we're going to say 6's to 5, just like we did in the last one, just as 9 is to Y. Okay, and remember, you always got to set up the proportion as if I go big to small with my first ratio, I got to go big to small with my second ratio. So that's why I went 6 to 5 and then came back and went 9 to Y. And if you look at the other ratio, the other ratios and the other proportions, they all go big to small also. So then I'm going to cross multiply divide. 6Y equals 45. 45 divided by 6 gives me 7.5. So I see that I just found EF was 7.5. All right, and that's how you find missing sides in similar figures. It's very straightforward, and you've probably practiced it a lot in your classes because that was one of the main concepts we learned way back in January. So next question, true or false, angle B is congruent to angle E. Well, I don't even need to look at the picture, and I know that this is true because if you look at the picture, B and E are in the same position, which means they correspond. And if we remember something about what we said in the beginning, corresponding angles of similar figures are congruent. So this is in fact true. And then what is the ratio of their perimeters? Well, that's very simple also. The ratio of the perimeters is the same as the ratio between the sides. So therefore my answer to part 4B is going to be 6 to 5. That's problem 1 through 4, and that's a very good example. You could try the ones in your packet now, even though that they're not the same numbers. Okay, what theorem or postulate, this is number 6, and again I changed things around. It's not exactly like the one in your packet, but it uses the same concepts. What theorem or postulate would you use to prove triangle ABC is similar to triangle EBC? So there's some ways to prove triangles similar. First is side, side, side. You need to prove all 3 pairs of corresponding sides have equal ratio, and that's the first way to prove triangles are similar. The second way to prove triangles are similar is side angle side similarity. And you recognize, yeah, we did this in first semester with congruence, but now we're not talking about similarity. We're not talking about sides being congruent. We're talking about corresponding sides have equal ratios, or corresponding sides are going to be proportional. All right, the third and final way to prove triangles are similar is by angle-angle similarity. Okay, so let's look at, and it should say 3, so let me just correct that. So angle-angle similarity. So I'm looking at this picture and I'm thinking angle-angle similarity. Okay, I'm thinking angle-angle similarity for the mere fact that I don't know anything about the sides. Okay, I don't know that the sides have, usually the sides would have numbers and I could prove that the ratios are congruent. I don't know anything. So let's see if we can do angle-angle, and in fact when we look at this problem it's pretty simple. Vertical angles are congruent. So I got one angle congruent to one angle in the other. I got the vertical angles congruent. So these 2 triangles are actually going to be similar by angle-angle similarity. Okay? If it was going to be side, 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 or side, angle, side, you'll be given some numbers on the sides, and you'd be able to prove that their ratios were going to be congruent. Okay. Next question. All right, here's a good one. This is a typical problem that you probably saw in your test, and you're going to see on the final. And you got to use the following diagram to prove, or to find actually, CE and DE. In this particular picture, whenever you have a third side, or third line, because you got the 3 sides of a triangle, and you got, a 4th line, in this case, this line, parallel to one of the sides of a triangle, it creates 2 similar triangles, okay? If you can go all the way back to chapter 3, and remember, if lines are parallel, then corresponding angles are congruent, then triangle ABC would be similar to triangle DAE by angle-angle similarity, just like we showed in the last one. So we could do that, but we should be able to look at this problem and just realize, okay, I know this got similar triangles and I got to set up proportions. So I'm going to find CE and DE. Okay, tips to triangles like this is, I always tell students to make sure that you use entire sides and then separate the triangles if needed. Okay? The second thing is to set up proportions using the entire sides. Do never use part of a side. BD is part of a side. CE is part of a side. I don't ever want to use those when I'm setting up my proportions, okay? So I need to find 2 things. I need to find CE, which I'll call X, because that's the first thing I wanted to find, and I need to find DE, which I'll call Y. So those are basically what I'm looking for, is X and Y. So my tip is I'm going to separate these triangles, okay? And with the smartboard, this is really easy. But you could just as easily draw it on your paper. If I take this triangle out, okay, I see that this side was 4, this side was 10, and that side was 7. Okay? When I do that, I'm going to erase the stuff inside, because now I'm left with this little triangle that's got sides of 4, 7, and 10, and I got this big triangle that's got different sides. Okay? So instead of leaving it as 4 and 6, I'm actually going to erase these. And if you miss what I do here, 4 and 6 makes 10. So if you want to rewind or whatever and look back at that, you can see that. I'm actually going to erase these as well. I know that was 7 and X, and 7 and X together is going to be 7 plus X. So now it's pretty straightforward. If I'm going to find CE, well, that is actually X in this particular case. So CE is X, and I'm going to set up my proportions. So to find CE, I got 10 over 4 equals 7 plus X over 7. You cross multiply, divide. When I cross multiply here, I got to make sure I distribute the 4. 4 goes to 7, 4 times 7 is 28, 4 times X is 4X. 7 times 10 is 70. Okay, subtract 28 from both sides. 4x, 70 minus 28. So I don't make a dumb mistake. It's 42. And the x is going to be 42 divided by 4, or 10.5. So CE has got to be 10.5. DE you find in a very similar manner, okay? Now that I got the triangles separated, these problems become easy. So make your life easy, find DE now. DE is y. So I'm going to set up the proportion. I'm going to say, I'm use the same ratio that I used, just straight I'm talking about, I'm going to use the same ratio. Similar figures, right? We're using the same ratio. So I'm going to say 10 over 4. And that's going to equal DE, which is y, over 10. So now when you cross multiply, you get 4y equals 100. Y equals 25. So that's my answer to DE. And you see how easy it becomes when you separate the triangles out. I know it's often a step that students like to skip, but it does make it a lot easier in this case. Again, feel free to rewind, watch my steps, and see what I did. But that's the way I teach it. Some of your teachers might teach it differently. You could ask them if you watch this, how they would explain this. All right, the next question is not a triangle, it's not a figure, but it does use proportions, and that's why it falls in this chapter and falls under this section. So first thing, I want to make sure that the ratios in the proportion use corresponding parts. Well, in my picture here, I'm given that BH is 20. I'm also given that AC is 6, CE is 7, and EG is 3. So what I'm looking for BD. So my first question is BD. So I'm going to call that X. And when I talk about use corresponding parts, I talk about using the corresponding parts. In this case, X corresponds to 6. So that's the first ratio I'm going to say. So I'm looking for BD. BD is X. X corresponds to 6, just as, and I got to find another ratio. The only ratio I can come up with is 20 corresponds to this whole part, which is 16. All right? So I could say 20 over 16. If you want to reduce 20 over 16 to a smaller fraction, you may do that. I'm just going to cross multiply, and that's going to give me the same answer. So 6 times 20 is 120. 16 times x is 16x. 120 divided by 16 gives me 7.5. So that's the answer for BD. Okay? Next question, DH. Well, DH is this piece here. We'll call that y. Well, I'm going to say y corresponds to this whole part, which is 7 plus 3, or 10. So y corresponds to 10, and I'm going to use, just like we do with similar figures, in this case you got parallel lines cut by a transversal. I'm going to use the same ratio that I used in the last one, which is y is to 10 as 20 is to 16. You cross multiply 200 equals 16y. Divide both sides by 16. Just to show you that step, I've been skipping that step, but that's how you find that y is 12.5. So I got x was 7.5, x represented BD, I got y was 12.5, y represented DH, and that's how you would do a problem of 3 or more parallel lines cut by 2 transversals. Okay, that was a concept from chapter 8.6. The last question I want to talk about is the angle bisector theorem. And again, this is the 8.6 concept, and the way that I teach this is you start it anywhere. Okay, if you see a picture like this where it says it's an angle bisector, you got 4 parts. What I mean by that is you got this part, and then you got the sides. I'll just highlight this one. Here. Okay, you got the 4 parts. Any way that you set this up should work for you. Okay, I'm going to start with the 8. Okay, I can go anywhere. I'm going to go to the 3. 8 over 3. And then I got to set it up, like I said, in a zigzag fashion and go 12 over x. So 8 is to 3 is 12 is to x. If you set the zigzag fashion up, you get it with 8x equals 36. 36 divided by 8 is 4.5. Again, divide both sides by 8. X equals 4.5. And just to show you that you have a lot of freedom with these problems, I can start anywhere. Again, I'll start with the x. Okay? So x goes to 3, for example. If I zigzag back, again, I got to zigzag back to the 12 and finish with the 8. So I'll say x over 3 equals 12 over 8. right away, you already see that your cross products are the same. So I don't even need to finish this problem because you got the exact same thing. You're going to get x equals 4.5 no matter how you do it if you set up the ratio, the proportion in that zigzag fashion. I hope that this helped, and hopefully you'll do well on this part of the final. And again, feel free to use your review packet to go along with the same numbers because they're basically the same, except I just changed the numbers within the problems. Okay, next.